What if I told you that somewhere inside our own galaxy, hiding in plain sight, there's an object so violent, so unimaginably powerful, that it can hurl tiny pieces of matter across space with more force than every machine humans have ever built combined? And here's the strangest part. Until very recently, nobody even knew this thing was real. Scientists suspected, they guessed, they argued, but the proof kept slipping through their fingers like smoke. Before we go any deeper into this mystery, do me one small favor. If you love space, if you love the feeling of learning something that most people on Earth still have no clue about, tap that like button, hit subscribe, and share this video with one person who always looks up at the stars and wonders what is really out there. That tiny action helps this channel more than you can imagine, and it keeps these deep space stories coming straight to you. Now, let us step outside for a moment. Picture yourself standing in a quiet field at night. The sky looks calm. The stars look still. Everything feels peaceful and far away. But that peace is a lie. Right now, as you breathe, invisible bullets of energy are hitting your body, your house, your city, your entire planet. They come from every direction. They never stop. They are so small you cannot feel them, but they are so fast and so energetic that they can knock satellites offline, scramble sensitive electronics, and even cause tiny changes inside living cells. These invisible bullets are called cosmic rays, and for more than 100 years, they have been one of the greatest unsolved mysteries in all of science. Scientists knew they were there. They could measure them, they could count them, but nobody could answer the simplest question of all. Where do they actually come from? What kind of monster in space is strong enough to fire them at us? For decades, that question had no real answer. Only theories, only guesses, only silence from the stars. But that silence has finally been broken. And what scientists are now finding is stranger, wilder, and far more powerful than almost anyone expected. To understand why this discovery matters so much, we have to go back to the beginning. Our galaxy is a place full of light, but the light you can see with your eyes is only a whisper of what is really out there. Beyond visible light, there are other kinds of radiation flying through space. X-rays, gamma rays, streams of charged particles moving so fast they blur the line between matter and pure energy. These forms of radiation are like footprints. They're the fingerprints left behind after something violent happened, somewhere in the cosmos. If you can read those fingerprints carefully, you can start to understand what kind of events made them. And among all these fingerprints, one type has puzzled scientists more than any other: cosmic rays. The story really begins in 1912, over a century ago, when a curious Austrian physicist named Victor Hess did something almost nobody was brave enough to try. He climbed into a hot air balloon and rose more than 5 kilometers into the sky, carrying delicate instruments designed to measure how strongly the air around him was becoming electrically charged. At the time, most scientists were sure of one thing: if you go higher, the effect should get weaker because they believed the radiation came from the ground beneath our feet. But what Hess found flipped everything upside down. High in the sky, the radiation was not weaker. It was about 3 times stronger. That single balloon ride changed the direction of physics forever, because it meant only one thing: the radiation was not coming from Earth, it was falling on us from space. That was the moment cosmic rays were discovered, and ever since then, they have kept crashing into our atmosphere without pause. These particles are mostly protons, tiny pieces of matter, but they travel almost as fast as light itself. When they hit the upper atmosphere, they explode into showers of smaller particles that rain down on us silently, every second of every day. Some of those secondary particles can pass through walls, through metal, even through you. Over long periods of time, they can damage cells, cause mutations, and slowly wear down electronics floating in orbit. Astronauts feel the effect strongest. Their DNA takes real hits. Their equipment fails more often. Even here on the ground, cosmic rays occasionally flip a single bit inside a computer chip, causing strange and unexplained glitches. So these particles are not just some quiet background noise of the universe. They shape technology, they shape biology, they shape the invisible weather of our planet, and yet, for more than 100 years, we could not figure out where the strongest of them were being made. The reason is heartbreakingly simple. Cosmic rays are charged particles, and charged particles do not travel in straight lines. Space is filled with magnetic fields that twist and bend their paths. So by the time a cosmic ray finally reaches Earth, it has been pushed and pulled 1,000 times over. It arrives from every direction at once, giving away no honest clue about its true home. Imagine trying to figure out where a bullet was fired from after it bounced off 10 different walls. That is what scientists were dealing with. Now, if you are still with me, and I really hope you are, take a second and drop a comment below with the word cosmic. I want to see how many curious minds are watching right now. It genuinely helps this video reach more people who love space, and it means a lot to me personally. Now back to the mystery. Scientists tried a different trick. Instead of tracking each cosmic ray one by one, they started drawing a giant graph. On one axis, they put energy. On the other, they put how many particles arrive at Earth carrying that energy. What they found was strange. The graph did not slide down smoothly. There was a sharp bend in it, a sudden change in the curve, a place where the number of high-energy particles suddenly dropped in a way that did not look natural. They gave this bend a simple name, the knee. Beyond the knee, cosmic rays became rare, very rare, almost impossibly rare. Some scientists said this bend was the border between particles born inside our galaxy and particles arriving from faraway galaxies. Others said no, it was something else. Nobody could prove it. The knee sat there for years, like a locked door, and nobody had the key. Then, high in the mountains of Sichuan province in China, at nearly 4.5 kilometers above sea level, humans built something that would finally begin to unlock that door. It is called the Large High-Altitude Air Shower Observatory. That is a mouthful, so most scientists just call it LHAASO. The idea behind LHAASO is simple to describe, but insanely difficult to build. It is trying to catch the highest energy particles anywhere in the entire universe. To do that, you need two things. First, you need a truly gigantic detector, because the strongest cosmic rays are so rare that fewer than one hits every square kilometer of Earth in an entire century. So if you want to catch them, you have to cover an enormous piece of ground. LHAASO covers an area roughly the size of 190 football fields. Stop and think about that. 190 fields, all lined with sensitive detectors, all watching the sky every second. And second, once you catch a particle shower, you have to figure out what kind of particle actually caused it. Was it a proton? A helium nucleus? Something heavier? To answer that, LHAASO uses at least 3 different types of detectors working together at the same time. They cross-check each other, they compare notes, they rebuild the story of what came crashing into the sky, and when they finally switched this monster on, something happened faster than anyone expected. Even before construction was finished, only half of LHAASO was running, and yet it was already picking up far more high-energy gamma rays than anyone had predicted. By 2021, it had detected gamma-ray photons with energies above 1 quadrillion electron volts. That word, quadrillion, has 15 zeros in it. One of those photons carried an astonishing 1.4 quadrillion electron volts of energy. It was the highest energy photon ever directly measured by human instruments. To help you feel just how insane that is, compare it to the Large Hadron Collider in Europe, the most powerful particle accelerator we have ever built. That single photon carried about 150 times more energy than the fastest protons the Large Hadron Collider can produce. And it was made naturally, out there in space, by something we could not even see. That leads to a chilling conclusion. The laws of physics are strict. Energy cannot come from nowhere. If a particle carries that much energy, something out there had to give it that energy in the first place. Scientists had been theorizing about such an object for decades, a cosmic engine so violent it could boost tiny particles to unbelievable speeds. They gave it a name, a Pevatron. A Pevatron is any object in space that can push particles up to the peta-electron volt range. In plain words, up to 1 quadrillion electron volts and beyond. For years, Pevatrons lived only inside equations. Now, thanks to LHAASO, they were suddenly real. But knowing they exist is one thing. Finding them is a whole different battle. Luckily, gamma rays give scientists one huge advantage. They have no electric charge. That means they are not bent by magnetic fields. They travel in perfectly straight lines, which means if you catch one, you can look back along its path and know the direction it came from. Using this trick, LHAASO scientists mapped their catches across the sky and slowly, carefully, they marked out 12 distinct sources of ultra-high energy gamma rays, 12 strange spots in the heavens, 12 possible homes for Pevatrons. But still, there was a problem. Direction is not the same as distance. 12 lines pointing outward could stretch across the entire universe. So how did they narrow it down? Here is where physics saved the day. Since the Big Bang, the entire universe has been filled with a soft glow of very low energy photons. It is like an ancient light bath left over from the birth of everything. Now, when a high-energy gamma ray tries to travel through this bath for too long, sooner or later it will slam into one of those old photons and be destroyed. That means gamma rays with these extreme energies cannot travel across huge cosmic distances. They simply do not survive. And that changed everything. Because if LHAASO was detecting them, they could not have come from far-off galaxies. They had to be nearby. They had to be inside our own Milky Way. Just like that, two mysteries snapped into focus at once. The knee in the cosmic ray graph. It had nothing to do with distant galaxies. And the 12 mysterious sources, they were all right here in our own cosmic backyard. The hunt for the most powerful objects in the galaxy was officially on. If you are still enjoying this, I have a small challenge for you. Pause for one moment. Take a screenshot of this exact part of the video. Post it on your favorite social platform and tag anyone who says space is boring. because nothing about this is boring. And a share from you helps this story travel further than any gamma ray ever could. Now let us dive into the suspects. Long before LHAASO existed, scientists already had a few candidates in mind for these cosmic monsters. Space is full of violent places, but only a small handful were even theoretically capable of accelerating particles up to Pevatron levels. For nearly 70 years, one main suspect held the spotlight: supernova remnants. When a giant star reaches the end of its life, it does not fade quietly. It explodes with enough force to briefly outshine an entire galaxy. What is left behind is a huge cloud of debris expanding outward, torn open by shock waves and roaring with energy. On paper, supernova remnants have more than enough power to be Pevatrons. If just 10 to 20% of their energy went into speeding up particles, they could easily explain most of the cosmic rays we detect. And the mechanism sounds elegant. When the exploding shell of gas smashes into surrounding space, it creates a sudden wall where pressure, density, and magnetic fields all shift violently. A particle caught near that wall gets bounced back and forth across it, gaining a little more energy with every crossing. This process is called diffusive shock acceleration, sometimes called the Fermi mechanism, and it can go on for centuries. But there is a catch. The math suggests that supernova remnants can only reach true Pevatron levels during the first 100 years or so after the explosion. And every supernova remnant we currently know of is much older than that. So the timing does not quite line up. There's a possible workaround. Even after the main shock has slowed down, particles that were boosted inside the remnant might escape into nearby giant clouds of gas. When they hit those thick clouds, they can produce gamma rays with quadrillion electron-volt energies, even long after the original explosion is cooled off. So supernova remnants stay in the running. Researchers believe up to 6 of the 12 original LHAASO candidates could be linked to them, but interestingly, they are not the leading suspect anymore. There is another kind of object that many scientists now think is even more likely: pulsars. A pulsar is a small, dense, rapidly spinning corpse of a star. When certain giant stars die, their cores collapse into an object only about 20 kilometers wide, but heavier than the sun. That tiny leftover core spins at incredible speeds, sometimes hundreds of times per second, and it carries a magnetic field so intense that it distorts space around it. Right now, more than 1,500 pulsars have been discovered in our galaxy alone. And these things are already known to be extreme particle accelerators. Their spinning magnetic fields create electric fields powerful enough to rip charged particles right off their surfaces. That creates a rushing wind of high-speed particles blasting outward. When that wind slams into surrounding gas or old supernova debris, it hits a wall, slows down, and forms what is called a termination shock. That shock is another perfect place for particles to be boosted to insane energies. So pulsars are not just candidates. Many scientists now think they might be the main engines behind our galactic Pevatrons, but then a third suspect stepped forward, and it might be the strangest one of all. When researchers looked more carefully at the shape of that cosmic ray energy graph near the knee, they noticed something odd. It was not a smooth curve. There was a small bump, a little wrinkle in the data that supernova remnants and pulsars alone could not fully explain. That little bump forced scientists to consider something wilder: black holes. The idea that black holes could act as particle accelerators is not new. It was seriously proposed around 2009. In that scenario, two particles falling toward a black hole slam into each other right near the event horizon, the point of no return. In that tiny spot, physics goes wild. Under the right conditions, the collision could produce particles with almost unlimited energies. For a long time, most scientists shrugged this off. Any particles born that close to a black hole should just fall in, right? But newer models changed the picture. They showed that a meaningful fraction of those particles could actually escape. They could get flung outward, back into space, joining the ocean of cosmic rays flowing through the galaxy. Suddenly, black holes were not just cosmic vacuum cleaners. They were possible cosmic guns. If your mind is spinning a little right now, that is exactly the point. Because the deeper we dig, the more clear it becomes that our galaxy is not the quiet place it looks like. So, what have scientists actually confirmed so far? Finding 12 suspicious regions in the sky was only step one. Pinning down the exact object inside each region is a completely different challenge. It is like knowing a scream came from somewhere on your street, but not which house made the sound. Still, some houses have already been identified. One of the first confirmed Pevatron candidates is an object almost every space fan already knows: the Crab Nebula, also called Messier 1. It sits around 6,500 light-years away in the constellation Taurus, and it is the glowing wreckage of a star that exploded nearly 1,000 years ago. But the Crab Nebula is more than a pretty picture. It can accelerate electrons up to a full quadrillion electron volts. And because it is one of the most studied objects in the entire sky, it gives astronomers a rare front-row seat to how these natural machines actually work. In gamma rays, the Crab Nebula flickers. It sends out sudden bright flares that can last for a few hours or a few days. Now, with our new understanding of Pevatrons, scientists believe these flares are moments when the accelerator inside the nebula suddenly kicks into overdrive, pushing electrons to extreme energies in real time. Exactly what triggers these bursts is still debated. Maybe shockwaves near the pulsar wind, maybe snapping magnetic field lines that release enormous energy in an instant. Then there is that record-breaking photon. Remember the one carrying 1.4 quadrillion electron volts, the most energetic single photon ever recorded. Scientists were desperate to trace its origin. That hunt led them to the constellation Cygnus. Cygnus is one of the most famous shapes in the northern sky, stretched across a huge area. And inside it, LHAASO caught a rain of extreme photons streaming out from a strange feature nicknamed the Cygnus Cocoon. It is a giant bubble of glowing gas, surrounding a place where new stars are being born in huge numbers. Inside that bubble sits a dense young star cluster called Cygnus OB2. It is bursting with massive young stars, each one throwing off powerful winds of gas and particles. Those winds crash into each other and into surrounding material, forming the perfect conditions for particle acceleration. The cluster sits about 5,000 light years from Earth, and it lines up nicely with several of the gamma-ray signals LHAASO picked up. But there was a twist. Along the same line of sight, sitting much farther away, there is another beast, an object called Cygnus X3. This one is not a star cluster. It is a binary system, a pair. On one side, a massive hot star known as a Wolf-Rayet star, one of the fiercest kinds of stars in the universe, constantly blowing off its outer layers. On the other side, a mysterious compact object, most likely either a neutron star or a black hole, feeding on the material streaming off its partner. That donor star pours matter into its partner. The partner then launches jets of hot plasma back into space. Together, they create almost perfect conditions for a natural particle accelerator. So, which was the Pevatron? Cygnus OB2, or Cygnus X3. At first, telling them apart looked nearly impossible. But then researchers noticed something in the gamma-ray signal itself, a repeating rhythm. The signal pulsed with a pattern that repeated roughly every 4.8 hours. And that same rhythm showed up not only in gamma rays, but also in X-rays and infrared observations. Then it clicked. Cygnus X3 has an orbital period of about 4.8 hours. That is how long it takes the compact object to circle its massive companion. It was a signature, a fingerprint. It could only mean one thing. The gamma rays were coming from Cygnus X3, and when scientists measured the top photon energies from this system, they were staggering. Some photons carried up to 3.7 quadrillion electron volts. That is beyond a normal Pevatron. That places Cygnus X3 into a whole new class, a super Pevatron, an engine capable of pushing particles to at least 10 quadrillion electron volts. Read that number again and let it sink in. This is happening right now, thousands of light years away. And pieces of that energy are still arriving at your planet every single day. Take a slow breath. Because here is where things get even bigger. 12 candidate sources sounded like a huge discovery when it was first announced. But that was only the beginning. In 2023, researchers published the first global catalog of galactic Pevatron candidates. It listed 43 confirmed ultra-high energy gamma-ray sources. Since then, that list has kept growing. Today, more than 75 candidates have been identified across our galaxy. Let me pause here and ask you one honest thing. If this is blowing your mind even a little, please help me out by clicking that like button one more time. Every single click tells the algorithm to show this story to more curious minds. And if you have not subscribed yet, now is the moment. This channel lives and breathes on viewers like you who actually care about the truth of the universe. That is a small favor, but it means the whole world to what I do here. Now think about the deeper meaning of 75 candidates. For decades, many astronomers thought the Milky Way was a fairly calm galaxy. It does not have a wildly active supermassive black hole at its center like some other galaxies. It seemed like a peaceful spiral. This new research has shattered that image. Our galaxy is not calm, it is roaring. It is filled with more natural Pevatrons than we ever imagined. It is stitched with hidden engines of extreme energy, hiding inside star clusters, pulsars, remnants, and binary systems. The Milky Way is not sleeping, it is thundering, quietly, in a language only gamma rays can speak. And LHAASO is not doing this alone. It is working hand in hand with other high-energy observatories around the world. There are teams in the United States, in Germany, in Namibia, in Spain, all watching different parts of the sky. When several observatories in different countries independently see the same signal from the same region of sky, that is when scientists can say with real confidence, yes, this is real. This is not a glitch. This is a genuine cosmic accelerator burning at the extreme edge of physics. And which brings us to a question that has probably been bubbling in your mind. How does LHAASO actually catch these particles? Because when a cosmic ray or a gamma ray hits our atmosphere, it does not just stop, it shatters. That single particle explodes into a cascade of secondary particles, a cone-shaped storm called an extensive air shower, which grows and spreads as it falls toward the ground. By the time this invisible waterfall reaches the surface, it can be hundreds of meters wide. That is why LHAASO has to be so gigantic. A small detector would only see a sliver of that shower. But by spreading thousands of individual detectors across an area the size of 190 football fields, LHAASO catches the footprint. Then, using powerful math, scientists can reverse the process. They trace the shower back through the sky, calculate the direction it came from, and estimate its energy. To make this even more precise, LHAASO combines several types of detectors. Ground-based particle detectors record the timing and spread of the falling shower. Water-based tanks catch a special glow produced during the shower, helping tell the difference between gamma-ray showers and cosmic ray showers. And then there are wide-field Cherenkov telescopes, capturing the faint blue flashes of light produced when charged particles move faster than light does through the atmosphere. That effect is real, and it leaves a shimmering trail that another detector can catch. When all these methods agree, when they see the same shower from different angles, that is when researchers can trust. That is why LHAASO's identifications are so much stronger than earlier attempts. It is not one detector guessing. It is a whole orchestra of instruments confirming each other in real time. And this is where the sheer scale of what has happened really sinks in. Before LHAASO started publishing results, the entire field had only a small handful of confirmed sources, collected slowly, painfully, over decades. Within its first year of only partial operation, LHAASO alone matched or beat that historical total. And within a few short years, it pushed the count past 75. That is not just adding data points. That is rewriting our picture of the sky. Because if Pevatrons are that common, then they are not weird exceptions. They are a normal, expected outcome of certain conditions in space. Wherever you find massive young star clusters, or fast spinning pulsars, or compact objects locked in tight dances, you may also find natural accelerators far more powerful than anything humans will ever build. And this matters far beyond astronomy. It touches the deepest questions in physics itself. How does matter behave when it is pushed to conditions we cannot recreate? What happens to space and time under those extreme energies? Are there unknown particles hiding out there, only born inside these violent cosmic engines? Every human-built particle accelerator, no matter how expensive, will eventually hit a limit. But nature does not care about our budgets or our engineering. It just does it. Out there, in the quiet dark, natural machines are already running at energy scales that we may never reach. And now, for the first time, we can watch them. We can measure them. We can begin to understand them. Think about that for a second. Every night, when you go outside and look up, there is an ancient, silent violence pouring through your body. Countless tiny particles, some of them born inside the wreckage of dying stars, some inside the wild magnetic fields of pulsars, and maybe even some born on the trembling edge of a black hole. All arriving from thousands of light years away, all whispering the same secret, that the universe is not calm. It only looks calm to us. It is filled with engines that burn hotter, spin faster, and strike harder than anything humans could ever dream up. And somewhere out there, in the constellations of Cygnus and Taurus, in bubbles of glowing gas and pairs of doomed stars, are the most powerful natural objects ever discovered. They have been running for millions of years, maybe billions. They will keep running long after every human machine has rusted into dust. But at last, we have started to see them. At last, we have started to hear them. And this is only the beginning. If this story moved you even a little, if it made you feel small in the best possible way, do not close this tab yet. Because there are more discoveries coming, more secrets breaking loose, more cosmic monsters waiting to be named. Subscribe now, share this with someone who deserves to feel the same wonder, and keep looking up, because the universe is talking. And finally, we are learning how to listen.